Hi, my name is Viacheslav Natarovskii and welcome to my talk, Wasserstein contraction and spectral gap of simple slice sampling. First of all, I would like to mention that this is the joint work with Daniel Rudolph and Björn Sprung. Okay, let's start. The outline of my talk is as following. I will start with the general sampling problem. Then I go to our algorithm, to the simple slice sampler. Afterwards, I move to the spectral gap and the Wasserstein contraction for the specific class of densities. And finally, I will present the main result. Okay, let's start with the sampling problem. Suppose you would like to sample with respect to some probability distribution pi, which has a density rho. Strictly speaking, it's not a density because it's unnormalized. Therefore, we have here the normalizing constant in the denominator. And the general idea of sampling is, for example, to use a Markov chain Monte Carlo method. What does it mean? You basically run a suitable Markov chain which has the limit distribution pi, and then you just stop after some steps and return the nth value of your algorithm. The question is also, how can you measure the error of the algorithm? One possible option is the so-called total variation distance. Here we just have to, we would like to measure the distance between the distribution of the nth step of the algorithm, and so how far is it from our goal distribution pi. I also would like to add here some important notation to this window. For example, d for dimension and rho for our unnormalized density. This some important notation that I will use during my talk. Okay, let's move to our algorithm, to the simple slice sampler. Firstly, I would like to present it in a very simple scenario, in one-dimensional case. Suppose you have this 2-peak density and you start at some point x1 here. So for the simple slice sampler, you firstly need to evaluate the value of the density at the point x1, it's here. Then you have to draw uniformly on this interval between 0 and rho of x1, and you end up somewhere here, for example. Afterwards, you have to find the so-called level set, which is basically the set of all x's where the value of the density is at least t1. And finally, you draw uniformly on this level set. You end up here, for example, x2. We can go on. And for x2, firstly, we have to calculate the value of the density at this point. It's here. Then we have to draw uniformly on this interval. For example, here, t2. Then we find a level set and then sample uniformly here, x3. Okay, that's the general idea. Let me formulate it. We need the definition of, as I said, of this level set. We will call it g of t. This is, as I said, just the set of all x's where the value of the density is at least t. I will also add it here. Okay, and simple slice sampler, as I said, for one iteration from xn to xn plus 1, it has just 2 steps. Firstly, you draw uniformly a level t between 0 and the value of the density at the current point, and then you draw uniformly on the level set corresponding to the level t. That's it. Okay, let's move to the convergence. So the spectral gap and the Wasserstein contraction. From the simple slice sampler, we call the Markov chain is called xn, and the corresponding transition kernel we call u rho. I will also add it here. But for u rho, we use also the notation for the corresponding Markov operator on L2 with respect to pi, to our goal distribution. And then we can define the spectral gap of this Markov operator by this formula. So it's basically 1 minus the operator norm of u rho minus the expectation operator with respect to pi, which is defined in this classical way. So why is it actually so interesting to take a look at the spectral gap? Because if we show that the spectral gap is strictly positive, then we have a geometric convergence in terms of total variation distance, which is quite well. Okay, but for the spectral gap, we need the Wasserstein contraction. So firstly, I will define Wasserstein distance. It's just the classical first Wasserstein distance with respect to classical Euclidean distance here. And why is it so interesting to take a look at the Wasserstein distance? Because if we show the so-called Wasserstein contraction, which is defined in this way, then we have the positive spectral gap. So remember, you have Wasserstein contraction, then you have a spectral gap, then you have a geometric convergence in terms of total variation distance. Okay, so can we show for some specific densities this Wasserstein contraction? And fortunately, the answer is yes. Firstly, we show this for the so-called log-concave rotation in varied densities. These are the densities which can be represented in this way as e to the minus phi of the norm of x. Since it depends only on the norm of the vector, that's why it's rotation invariant, first of all. And secondly, on the function phi, we have two conditions. First is that it's strictly increasing, which means that then the density goes to 0 when x goes to infinity. And then phi must be convex, which means that the rho is then log-concave. And for this specific class of densities, we have the Wasserstein contraction with the coefficient d over d plus 1, which is less than 1. And therefore, we also have a spectral gap, positive spectral gap. And therefore, also the geometric convergence. Okay, now I will show you how we manage to generalize this result onto some bigger class of densities. But for that, I will need one extra notation, and this is the level set function. It's not so complicated. That's just the volume of the corresponding level set. As remember, level set is the set of all x's where the value of the density is at least t. I will also add the notation, the definition of the level set function to the right window. And we managed to show a very important result that if we have two different densities but with the same level set function, then they have the same spectral gap. So the spectral gaps are equal for the simple slice sampler for both of these densities, which is a very good result because we can now generalize our previous theorem to all densities with the same level set function. Let me illustrate it shortly. Suppose you have this density. This is actually like the maximum of two Gaussian densities. It's not rotation invariant, I would like to mention. Then you can calculate the level set function. It looks like this. And for that concrete level set function, you can construct, for example, this density, rho 2, which has exactly this level set function. And even in other dimensions, like rho 1, for example. And what's interesting that all these three density functions, they have the same level set function. And which what means that, for example, for this density, we cannot apply the previous theorem, but maybe for this one or for this one. And then we have the estimate for the spectral gap, and since they are all equal, we have it for all of this density. So this is the general idea, and to you more formally, I will present it as my main result. So we we say that the level set function belongs to the class lambda k if the following function phi k, this very big guy, don't be scary, we define it in this way just to have that if we define rho k as e to the minus phi k, then this rho k will have exactly the level set function L. And we say that L belongs to the lambda k if this constructed function phi k, firstly, it's strictly increasing, and secondly, it's convex. That's quite easy to see that then we can apply the previous theorem. So we have our main result that if L belongs to the class lambda k, then we have an estimate for the spectral gap. What's important to notice here is that we have here another letter k because it's not a dimension of the density anymore. It can be some other number. And also what's interesting that actually that there is a good question whether you can check these conditions. It looks quite complicated, but we have some good theorems on how to check this using some smoothness of the function L, which I would be happy to discuss it maybe with you if you have some questions. Okay, that's it. Thank you for your attention. And here's actually our preprint. You can find any details there. Thank you. Bye-bye.